Venus, Earth's hellish twin Venus, the second planet from the Sun and Earth's nearest planetary neighbor, presents one of the most extreme and inhospitable environments in our solar system. Despite being similar to Earth in size and mass, earning it the nickname Earth's twin, Venus represents a cautionary tale of runaway greenhouse effects and atmospheric evolution gone awry. This brilliant celestial object, the third brightest in our sky after the Sun and Moon, has captivated human observers for millennia, while concealing beneath its cloudy veil a world of unimaginable hostility. Physical characteristics and size, Venus closely matches Earth in fundamental physical properties, making their comparison both fascinating and instructive. With a diameter of 7,521 miles, Venus is only about 400 miles smaller than Earth, while its mass equals roughly 82% of our planet's mass. This similarity in size and density suggests that both worlds formed from similar materials in the early solar system and likely began their evolutionary paths under comparable conditions. The planet's internal structure mirrors Earth's basic design, consisting of an iron-nickel core surrounded by a rocky mantle and crust. However, Venus lacks the magnetic field that protects Earth from solar radiation, possibly due to its extremely slow rotation rate or differences in core dynamics. This absence of magnetic protection has allowed solar wind to gradually strip away lighter atmospheric components over billions of years, contributing to the planet's current atmospheric composition. Venus orbits the Sun at an average distance of 67 million miles, placing it well within the habitable zone where liquid water could theoretically exist. This positioning makes Venus's extreme conditions all the more remarkable, demonstrating how atmospheric processes can completely transform a potentially habitable world into a hellish landscape. Atmospheric composition and the greenhouse effect. Venus possesses the densest atmosphere of any terrestrial planet in our solar system, with surface pressures reaching 92 times that of Earth, equivalent to the pressure found nearly 3,000 feet underwater in Earth's oceans. The planet's atmosphere creates the most extreme greenhouse effect known in our solar system. Dense clouds of sulfuric acid located 30 to 40 miles above the surface trap heat with extraordinary efficiency. Solar radiation penetrates the atmosphere and warms the surface, but the resulting infrared radiation cannot escape back to space through the thick carbon dioxide blanket. This process elevates surface temperatures to a staggering 864 degrees Fahrenheit, hot enough to melt lead and making Venus the hottest planet in our solar system, even hotter than Mercury despite being farther from the Sun. The sulfuric acid clouds that shroud Venus create a perpetual overcast sky, reflecting about 75% of incoming sunlight back to space. These clouds form through complex chemical processes involving sulfur dioxide and water vapor in the upper atmosphere. The result is a planet completely hidden from direct optical observation, requiring radar and infrared instruments to penetrate the cloudy veil and study the surface below. Unique rotation and day-night cycle. Venus exhibits one of the most unusual rotation patterns in our solar system. The planet rotates extremely slowly on its axis, taking 243 Earth days to complete one rotation longer than its 225-day orbital period around the Sun. This means a Venusian day lasts longer than a Venusian year, creating a unique temporal relationship found nowhere else among the planets. Even more remarkably, Venus rotates backward relative to most other planets in our solar system, a phenomenon called retrograde rotation. While Earth and most planets rotate counterclockwise when viewed from above their north poles, Venus spins clockwise. This backward rotation may result from a massive impact early in the planet's history that literally knocked it over, or from complex gravitational interactions that gradually reversed its spin over billions of years. The combination of slow, backward rotation and the planet's thick atmosphere creates minimal temperature variation between day and night sides. The dense atmosphere efficiently distributes heat around the planet, maintaining relatively uniform temperatures across the entire surface regardless of solar illumination patterns. Surface features and geology radar mapping missions have revealed that Venus possesses a diverse and geologically active surface despite its hostile environment. The planet's terrain includes vast plains, towering mountains, deep valleys, and numerous volcanic features. Volcanic activity appears to be relatively recent in geological terms, with many lava flows showing minimal impact craters, suggesting they formed within the last few 100 million years. Maxwell Montes, Venus's highest peak, rises about 6.8 miles above the mean surface, level higher than Mount Everest rises above sea level on Earth. This mountain, along with other highland regions, demonstrates that Venus has experienced significant tectonic activity throughout its history. However, unlike Earth's plate Venus appears to undergo periodic global resurfacing events where much of the planet's surface is renewed through massive volcanic activity. The planet's surface shows evidence of both explosive and diffusive volcanism, with features ranging from small volcanic domes to enormous shield volcanoes. Crater analysis suggests that Venus's surface is relatively young, with most features dating to between 300 to 800 million years ago. This implies that the planet underwent a global resurfacing event that erased most evidence of earlier geological history. Exploration, history, and scientific discoveries. Venus has been the target of numerous space missions, making it one of the most studied planets in our solar system. The Soviet Union's Venera program achieved remarkable success in exploring Venus, despite the planet's extreme conditions. Venera 7 became the first spacecraft to successfully land on another planet and transmit data from the surface in 1970, followed by several missions that provided increasingly detailed information about Venus's atmosphere and surface conditions. The most successful surface missions, Venera 13 and 14, operated for over 2 hours on the surface in 1982, transmitting the first color images from Venus's surface and conducting detailed chemical analyses of the rocks. These missions revealed a landscape of flat, rocky plains under perpetually overcast skies, with rocks resembling basaltic compositions similar to those found in volcanic regions on Earth. NASA's Magellan mission in the 1990s revolutionized our understanding of Venus by using radar to map the entire planet's surface in unprecedented detail. These observations revealed the complex geological history of Venus and provided evidence for ongoing or recent volcanic activity. More recent missions, including the European Space Agency's Venus Express, have studied the planet's atmosphere and climate dynamics, revealing complex circulation patterns and chemical processes, atmospheric dynamics, and weather patterns. Venus's atmosphere exhibits some of the most extreme weather phenomena in our solar system. Despite the planet's slow rotation, winds in the upper atmosphere reach speeds of up to 250 miles per hour, circling the planet in just 4 Earth days. This phenomenon, known as superrotation, remains one of the most puzzling aspects of Venus's atmospheric dynamics. The planet's weather patterns are dominated by convection and global circulation cells that transport heat from the equator toward the poles. Unlike Earth's complex weather systems driven by temperature differences and the Coriolis effect, Venus's weather operates under fundamentally different physical constraints. Due to its dense atmosphere and slow rotation, acid rain falls continuously in Venus's upper atmosphere, though it evaporates long before reaching the surface due to the extreme temperatures. Lightning may occur in the sulfuric acid clouds, adding another dimension to the planet's hostile atmospheric conditions. These extreme weather patterns make Venus an important laboratory for studying atmospheric physics under conditions impossible to replicate on Earth. Implications for climate, science, and astrobiology. Venus serves as a crucial case study for understanding climate change and atmospheric evolution. The planet may have once possessed liquid water oceans early in its history, potentially making it habitable for billions of years. However, a runaway greenhouse effect transformed Venus into the hellish world we observe today, providing insights into how planetary climates can undergo irreversible changes. The study of Venus's atmospheric evolution helps scientists understand the factors that determine planetary habitability and the potential fate of Earth's climate under different scenarios. Venus demonstrates how a planet similar to Earth can develop along a completely different evolutionary path, emphasizing the delicate balance required to maintain habitable conditions. Recent discoveries of phosphine in Venus's upper atmosphere have sparked renewed interest in the possibility of microbial life existing in the planet's cloud layers, where temperatures and pressures are more moderate than at the surface. While controversial, these findings highlight the importance of continuing to study Venus as we search for life elsewhere in our solar system. Future exploration and scientific goals Several space agencies are planning ambitious new missions to Venus in the coming decades. NASA's Da Vinci Plus and Veritas missions, along with the European Space Agency's Envision, will provide unprecedented insights into Venus's atmosphere, surface, and geological history. These missions will use advanced instruments to study the planet's climate, volcanic activity, and potential for past or present habitability. Future exploration goals include understanding why Venus and Earth evolved so differently despite their similar starting conditions, determining whether Venus ever had liquid water, and investigating the planet's ongoing geological activity. Long-term objectives may include atmospheric probes capable of surviving in Venus' harshy environment for extended periods, and eventually sample return missions that could bring Venusian rocks back to Earth for detailed analysis. Venus continues to challenge our understanding of planetary science and climate dynamics while serving as both a cautionary tale and a source of scientific inspiration. This brilliant evening star, visible to the naked eye and celebrated by ancient civilizations, reminds us of the incredible diversity of worlds in our solar system and the complex processes that shape planetary environments. As we continue to explore Venus and unlock its secrets, we gain valuable insights into our own planet's climate system and the factors that make Earth uniquely suitable for life as we know it.